Oops, let me move this down a little bit. For those of you who know my work in interactive storytelling, I'm not going to be talking about that today. I thought I'd talk about some, I of course continue to do research in autonomous characters and drama management and story generation, but I wanted to talk about some newer work that we've just been doing the last 2 years on automated support for game design. So what is automated support for game design? What we're trying to do is build sort of game design assistants that can actually reason deeply about the mechanics of a game, the state evolution rules of a game, and answer questions and infer consequences of those state evolution rules. So it really is kind of achieving this vision would constitute an operational theory of game design. In a sense, you would have stuck kind of the knowledge that's in a game designer's head in a box, right? So you can think of it as that sort of would be the ultimate goal, would be to stick, everything a game designer knows about making a game into an AI program. But the goal is not to replace human designers. We're not trying to put human designers out of business, but to really support human designers and to move game design in some sense to a meta level, where game designers would be sort of specifying constraints and kind of higher level goals and constraints on their games, but not necessarily worrying about every little hairy detail of the game mechanics. So just to contrast what I mean by game design, it's different from level generation. So those of you who might have played Rogue or NetHack back in the day, that was the first game to have automated 2D level generation. And in fact, in Diablo and Diablo 2 are basically using a very similar algorithm for level generation. But here, the game mechanics are fixed. What happens when you encounter various creatures, the inventory system and so on. The rules for all of that are fixed, and what it's designing and really doing in kind of a random way, kind of random placement of rooms and encounters, is it's specifying kind of specific encounters and a specific level within which to carry out those mechanics. So designing a kind of an automated terrain or automated level would eventually be part of automated game design, but what we're really focusing on is more like the fundamental mechanics themselves. So therefore it's also different from work on city and terrain generation. So here's a screenshot from a automatic city generation system. So those kinds of systems are really focusing on the physical space, but not the mechanics that take place within the physical space. So what I'd like to do in this talk is to sort of motivate automated game design. Why would you even want to work on it as a research problem? What's interesting about it as a research problem? Describe kind of the different sorts of knowledge that you have to give such a system. Kind of a high level, kind of knowledge level description of game design mechanics. And then I'll briefly present a prototype that uses common sense reasoning to reason about thematic mappings, talk about some current and ongoing work on using event calculus to reason about game mechanics, and then end with a little bit of future work. So diving into why you would want to work on this problem at all, there's really sort of 4 big motivations that we have. The first is helping novice designers. So many people nowadays want to build small, expressive, or informative games. So and I'm sure this is true of many game design faculty, get several cold calls a month from people who call me up and are like, oh, I'm at the bicycle safety board and we want to make a game about bicycle safety. Can you help us? Or I'm a judge in LA. This is another real call I got. I'm a judge in LA and I've got some ideas for kind of intervening for youth interventions to help prevent street violence, and I've got a game idea. Can you help me make a game, right? So there's this sort of growing community of people who are not game designers, but they have some message they want to communicate through a game, and they don't know how to design games, and they're also usually disappointed when they learn about the sort of expense and time involved in creating even a simple game. Would it be possible to build sort of an assistant, a game implementation or a game design assistant that could help you kind of take the message, take the content you want to convey and sort of gamify it, right? Turn it into game mechanics. And this would be different than game implementation assistants. Systems like GameMaker and Alice are great for making the programming, for simplifying the programming problem of making a game, but they don't tell you how to design a game, right? What mechanics should you even include? If you're making a 2D RPG style game, how should the inventory system work? Those are the kinds of decisions that systems like GameMaker and Alice don't help you with at all. Assuming you've made all those decisions, they help make the programming easier. So I kind of have this vision of trying to like take Game Maker and stick this sort of like AI plugin in it that it helps you actually figure out what your game mechanic should even be, and sort of offers kind of ongoing design critique as you design your game. Another motivation is to help make prototypes more informative. So building kind of circles and boxes style prototypes is becoming more and more common in the commercial game design industry as a way to understand the interactions and mechanics at a really early phases of game design. So these are two prototypes from Spore. The Spore team was one of the first among the first game design teams to really use prototypes, like early prototypes, in a big way. They built probably over 100 of them in the first few years of the design of Spore. And you can see from these, like this is an example of a simple economy system prototype they were playing with. And this is an example of kind of a content construction prototype. And you can see that, the goal of prototyping here is not to build something that looks at all like the finished game, but rather to build, to render as simply as possible an interactive system that embodies some mechanics you want to try out. And so, and prototyping is a really powerful process for letting you explore and answer questions about game mechanics very early, without having to wait for the whole engine to be done before you can play test and so forth. And it's great that they allow this experimentation with raw mechanics, but they don't help designers think about the implementations. The implications of mechanics. So I would say that right now with early prototyping style design, there's sort of this build, play, and hope for insight loop. Right? You build one, then you play it yourself, you have people around the office play it, and you hope that in the process of playing it, you get some insight into your mechanics, whether they were good or bad. And if you don't, if you build a prototype, you play it, and you're like, I don't know what I really learned from building this prototype, then that's a failed prototype. Like, it didn't answer a design question. And in talking to some of the people who did rapid prototyping on Spore, it's really easy to build failed prototypes like that, where you build a prototype, you spend all this time making something, but it doesn't answer any design questions in the end. So wouldn't it be interesting if this prototype actually knew something about its game mechanics, like in this economy system prototype, if you could say like, given these mechanics, is it possible that a player could earn more than 5,000 resource in the first 5 minutes? Because if they could, there's probably some exploit in the system that I don't want. And if it is possible, give me a trace of what those player actions look like, right? Wouldn't it be great if you could sort of ask questions of the prototype? This is another kind of vision for automated game design support. A third is enabling new genres. Building, so there are certain game genres out there that really require rapid deployment in response to specific events. So these are two examples of news games, which, as I'm sure most of you know, is a very small but emerging genre of games that are really the game equivalent of editorial cartoons. That they're sort of rapidly deployed games that comment on specific news events. So this is, the Bush back rub game that was a commentary on that G8 summit, where Bush gave the German chancellor sort of an unwanted impromptu back rub. And so here you have, 3 world leaders. You run back and forth and back rub, and their little happiness meters are moving up and down. And it's really kind of a whack-a-mole game almost, right? Where you're trying to keep everyone happening. Here, this gentleman is very unhappy at this point, thinking about nuclear war. So we better go appease North Korea with a back rub, right? So that's an example. This is Ian Bogo's Bacteria Salad that came out the summer of all of those spinach, the spinach problems of last summer, I believe, right? The bacteria spinach problems. So the problem with news games, and the reason why they're not sort of a common genre, like why don't we see, the New York Times or the Wall Street Journal or something having, a page every day that's like 10 or 12 news games about the games of that day? Well, even these kind of small games are too hard to build manually, right? You're still talking about, a team of, say, Flash programmers, 2 or 3 Flash programmers working for, say, a few days to a week to build a game. And that's a single game, but there's new news items coming out every day. To really make news games a genre that actually works, you need to be able to rapidly build and rapidly deploy games almost instantaneously in response to news events. Other kinds of genres that might require this kind of like very rapid deployment are kind of something I call game-a-day customized games. I've got this idea that, oh, wouldn't it be cool if just like you have your calendar a day, your Far Side calendar a day or whatever, what if I had my, I'd hook my cell phone, dock it with my PC once a day, and get a little game based on, say, my analyzing my web and email traffic, and it would be a little game just about me and what's going on in my day that day. And I get one of those every day, right? Obviously, it's impossible to even imagine how you would do that if human game designers are doing the design. You need to somehow push a game designer into the box in order to enable these sort of rapid generation of highly targeted games. Educational games that are customized, radically customized, meaning the mechanics themselves change in response to specific learners. Not even possible unless you have a system that can sort of reason about design and mechanics. And finally, this is really a way to understand game design. Many people over the years in AI have commented, Herb Simon being a very vocal proponent of this, that programs are theories, right? A program is a theory of some domain. And so automated game designers can kind of serve the same role in understanding games as story generators have served over the years in understanding narrative. Story generators are basically operational theories of narrative structure, and to the degree that they fail, for example, then, like they generate narratives and there's things wrong with those narratives, then that tells you that, oh, we haven't captured everything yet that we need in a complete theory of narrative structure. This would be a way to kind of get a handle on game design as a design science by building operational theories of games. And there have been repeated calls in the literature for languages of game design, whether those are design patterns. Doug Church, back in 1999, had a Gama Sutra article on what he called formal abstract design tools, which was basically a call for people to start developing kind of design pattern languages, because game designers don't even have languages to kind of talk to each other with about game design, right? So one way to really try to build a formal design science of games would be to build programs that instantiate theories of game design. So those are for me sort of the 4 big reasons why I find this a great topic to work on. So what kind of role could an automated designer play with, or what kind of role could it participate in with respect to designers, players, and the game? So, one thing it could offer is design time assistance. And this is one area we're focusing on a lot now, where you have the automated assistant and the designer, and they engage in a kind of conversation with each other during design. Then, when you're happy, you deploy the game and a player plays the game. And this is what, in the abstract, I use the tag CAD for game designers, right? This is the CAD for game designers model, where you have the sort of design critic and design helper that engages the designer during design time. The per player customization model basically has the designer kind of engage in meta design, right? Kind of putting some knowledge and biases into a customizer. And then at playtime, the customizer is kind of customizing the game to the player, right? And then finally, you can imagine games like for news game generation, where there isn't online customization of the game to the player. There's just complete automated generation of the game as a function of some external signal like news stories. So those are kind of the 3 roles that we've been thinking about for automated game design. All right, so before you can even get started building such a thing, you have to have an understanding, or try to develop an understanding of what kinds of knowledge are even involved in game design, and what are the sort of fundamental processes of game design. And we've factored the game design process. This is from sort of talking to lots of game designers and reading lots of game design books and trying to understand what's common across all these depictions of game design. We have kind of factored out game design knowledge into 4 knowledge sources: abstract mechanics, concrete game representation, thematic content, and control mappings. So abstract game mechanics is really the raw state and state evolution of the game, independent of how you're going to visually depict it, right? So you can think of this, for those of you who have done game design using physical prototyping. And in physical prototyping of games, you often build sort of the board game or the card game version of the game, where you factored out real-timeness, you factored out visual representation, and it's just kind of raw player verbs and state evolution update. That's this phase, abstract game mechanics. Then there's concrete game representation, whereas you have the audio-visual representation of the abstract mechanics. So, for example, in your abstract mechanics, you might have a notion of a time limit. In your concrete game representation, well, is that time limit like a fuse burning down? And then when the fuse burns down, you're out of time. Is it a little clock that's counting down? Is it an object moving at a constant rate? And when that object moves at a constant rate and falls off a shelf or something, at that point you've run out of time. Those would all be ways of representing differently, in visual representation, the same abstract state concept of timer. Third, you have thematic content, which are real-world references in games, given kind of the abstract game mechanics and sort of visual representations of the state. What visual representations do you use for the objects in the game, right? Is this a game set in a bar? Is it a game, set in a dungeon? Is it a game set in a castle? What are the objects in, bars, dungeons, and castles? How do those impinge on or constrain or afford game mechanics? That's a thematic mapping problem. And finally, control mappings, how the player interacts with a game. So if we look at some examples, here's Tapper. I don't know how many people here have played Tapper. Okay, a few, well, 1, 2, okay, 3. Yeah, I used to play Tapper back in high school. In Tapper, this is sort of what I would call an order fulfillment game where you're kind of running back and forth, fighting against time as these angry customers march up demanding beers. You've got to run to the right tap, fill a beer, and slide it down to the customer. When the customer catches it, they move back a little bit on the bar. Then when the glass is empty, they shoot it forward, and you have to catch the glass before it falls off and breaks. And it gets more and more hectic as more and more customers come in, and you're running back and forth trying to fulfill all these orders. So here, you could see, the abstract state, the pure abstract mechanics might be something like there's sources for some kind of resource you're managing. There's sinks for the resource. There's time limits on how long you have to service a request for a resource. And we're not talking about, and at that point, there's nothing about customers. There's nothing about them moving. There's nothing about that there's 4 bars arranged that you're moving between. You imagine kind of the card game version of this. There's just sort of sources, sinks, time limits, and various kinds of time limits, right? Because there's the empty glass time limit, which is sort of a secondary service request that's issued after fulfilling the primary request for the drink. That would be the abstract game mechanics level of representation of this. Then we start talking about visual representations. So time limits are, in this case, represented by moving something forward at a constant rate along a line. And when it reaches the end of the line, you're out of time. Thematic mapping, obviously, we set this in a bar, right? Well, we could have set it in a restaurant, and like Diner Dash is sort of a similar game at an abstract game mechanics level, but set in a restaurant where you're running around at a table and picking up orders, right? But because it's set in a restaurant, that might push back on your mechanics and give you some new ideas for mechanics. Like if it was set in a bar where you're like giving drinks to people at tables. Well, people get up from tables, right? And so drunk people, in fact, might get up from tables. So that might give you the idea of having an abstract mechanic where you have to avoid drunk people while you're trying to serve the bar, right? Serve people at the tables, which is not something that would come up in this thematic mapping. So, and then finally, control mappings. We have an idea, here, like to fill up the drink, you actually had to push a button and then, if I remember right, release it at just the right time as it got near the top to put the head on, right? And so it wasn't just hit a button. It was sort of like hit a button and or maybe it was actually pull a tap. Yeah, you pull it down a tap and it would fill it immediately to a certain level. And then you had to pull it down again after it was at that level to tap it off with the head. And so it kind of gave you, but you could have done something where you had to repeatedly pump it, right? Or maybe where you just hit it once and it immediately gives you the whole thing with the head. That would be, well, those would be different control mappings onto the same player verb. So that's an example of how, of sort of factoring out those 4 knowledge sources as separately variable components. Now, this applies to complex contemporary games, right? So you can talk about the same levels of representation in a game like BioShock. You can talk about the abstract system for power-ups for your character, which in BioShock are the plasmids you get, but in System Shock, right, are these cybernetic updates. And in fact, BioShock is sort of borrowing System Shock's or building on System Shock's sort of power-up mechanic, but then giving it a new thematic mapping, obviously, and then extending the mechanics slightly. And so you see these sort of 4 levels of representation operating even in a complex contemporary game. Yeah, enough said. So the first slice we took at this problem was actually looking at thematic reasoning. So we wanted to focus on thematic design partly because there was so little work in the area. And it sounded kind of like the hardest thing. Like, how do you reason about what everyday items you might want to, how you map the everyday world into games? It sounded like sort of, the hard, crazy, open-ended thing. And so we thought we'd push on the hard, crazy, open-ended thing first, see if we could make any progress at all, and see what that told us about the problem. Existing systems, there's very few existing systems looking at automatic game generation. This is almost, the complete literature here. Most existing systems are focused on abstract dynamics. So, meta games, chess-like games, or balanced board games. So basically, board games and chess-like variants has been sort of focus for both automatic game playing and automatic game generation. Egg in 2000 sort of compiled abstract dynamics to an interface. And so you gave it a fixed description of an abstract dynamics that came from somewhere else. It didn't reason about that. And then it did some reasoning about how to try to map that abstract mechanics into an interface. And then, there's sort of level generation, various procedural content generation systems, and so on, which focus on generating sort of new representations for fixed mechanics, but no work sort of on reasoning about thematic design or game mechanics beyond balanced board games or chess-like games. So to give ourselves a domain to work in that might be tractable, we focused on WarioWare scale microgames. So how many people here have played WarioWare, like any of the WarioWare? Okay, a few people. So WarioWare in the original GBA version, and this carries through to the contemporary Wii versions, it consists of a series of rapid-fire microgames, where each microgame literally takes like 4 or 5 seconds to play. And this microgame is like catch the ball. And in fact, at the beginning, it says catch. And that's all. It's like, okay, catch. What do I have to do? This ball flies at you. You move and try to get that ball in the glove. You're done. If you've won the game, if you catch it, you've lost the game if you don't. Here, you have to sort of use your samurai sword to cut the stick in half, and there's this gauge going up and down, and you have to hit the button to swipe the sword when the gauge is up in the red as it goes up and down, and you have sort of 4 seconds or so, as represented by this fuse on this bomb, to do it. And WarioWare just throws a rapid-fire sequence of these microgames at you, where each microgame is like a pure mechanic with a single-player verb. So we're like, oh, this is perfect. This is like in a sense, like the blocks world of game design or something, right? We're getting down to kind of the brass tacks, the most primitive units, and it's all thematic mapping, right? There's very few distinct mechanics in WarioWare, but the same mechanics are kind of mapped over and over again onto different themes, and that actually makes it very engaging. And so this, we thought this is great because it's a microdomain that, unlike blocks world, like ordinary people care about it. Like there's actually like a commercial game, right, that's based on this level of microgame. And so you kind of get the dual win of small enough that you might be able to do something with it, and yet actually compelling for gameplay. So to decompose WarioWare for thematic design, we really considered games on 2 levels: the abstract, what we called abstract games, and concrete games. So an abstract game is really thematic and specifies high-level dynamics. So a person avoiding a car, a duck avoiding a bullet, a mechanic pumping up a tire are examples of abstract games. Now, a person avoiding a car, well, there might be a lot of ways to implement, jumping out of the way of a car, right? And that is implemented by concrete games, which are bundled templates of J2ME code. So we're actually sort of assembling, we have this nice little sort of J2ME class library for microgames that allows us to kind of assemble, it's more than templated code generation, because we're actually sort of doing, class library, we're taking classes and kind of, composing them and instantiating them in various ways, but it's a really rich framework for creating kind of a large generative space of microgames out of this class library. And so this is executable code that bundles dynamics, representation, and control mappings into sort of one black box. So you might have like first-person crosshairs where the player wins if she shoots sprite A, and sprite A is filled in, right? Or a 2D side view where player shoots sprite A and wins if she avoids sprite B for 5 seconds. Those would be examples of concrete games. So the generation problem then, as a thematic mapping problem, becomes generate abstract games that make sense and plug them into concrete games, where making sense is the sort of common sense reasoning problem that thematic mapping opens up. So if we look at the avoid abstract game, for example, the game space for avoider as an abstract game is attacker, something that's capable of attacking, attacks an avoider, something that's capable of avoiding, right? Instances in that abstract game space are like duck avoiding bullet or person avoiding car. Now, if you, in this abstract game space, instantiate a specific abstract game, duck avoids bullet, that could be refined as a shooter concrete game or a dodger concrete game. It's a shooter concrete game if the attacker is a projectile, for example. So you might have additional rules for how to refine this into a concrete game. It's a dodger concrete game for all attacker role fillers, regardless of the attacker. You can always use dodger, but shooter with the crosshairs can be used in particular if the attacker is a projectile. So this is just trying to, in an image, sort of visualize this distinction between abstract game spaces, instances of abstract games, and concrete games. So the thematic mapping problem now becomes a kind of a constraint satisfaction problem, where you have a number of common sense constraints on role fillers in your abstract game. So you're sort of reasoning over a universe of possible role fillers, which are, you know, objects in your real world domain, you know, things like ducks and guns and cars and criminals and etc. Monkeys, bananas. These are some of the things in our in our world of objects. And so you have all these objects, and you're trying to plug them into roles on your abstract game, and you have these common sense constraints on how you can fill roles. So for the attacker and avoider game space, I'll move over to this side, because I've been gesturing over there for a while. In our abstract avoider game space, we say that basically, well, something can fill the role of avoider if it's a hyponym in WordNet. That means it's a kind of animate thing. So non-animate things like a desk can't be an avoider. Like that's what we're saying with this constraint. A desk can't be an avoider, but a duck could be, right? Because it's a type of animate thing. And in ConceptNet, it has to be capable of receiving action, the attack verb, some attack verb, right? Which also happens to be the same attack verb that the attacker is capable of generating. Right, so this is how we start combining avoider and attacker together. Well, where's this knowledge coming from? That we know that, like, guns are capable of shooting and a duck is capable of being shot, right? That's like real-world knowledge we'd have to have from somewhere. Well, we're using ConceptNet as our common sense ontology. ConceptNet is a sort of, you know, medium-sized semantic network from the MIT Media Lab that was mined from the OpenMind repository. OpenMind was kind of a crowdsourcing attempt to, instead of doing what Psych's been doing, of having sort of 50 experts working for 20 years to really build this this really kind of very tightly organized, tightly and neatly organized ontology, which is powerful in various ways because it's so tightly and neatly organized. The OpenMind people said, well, we're going to do a different approach of making these web forums where people can type in any English sentence they want. Right? And we'll just have, like, thousands or hundreds of thousands of people do that, gather all those sentences, and then mine them for a semantic network. Right? So it's sort of a crowdsourcing approach to creating a common sense ontology. So ConceptNet is on the order of a few 100,000 nodes, like 1.2 million links. So that's why it's sort of a kind of a medium-size knowledge base. And it's very noisy. I mean, as you might imagine from people typing in things, you might not, like the fact that duck is a bird, for example, might not be in ConceptNet, but the fact that Mikey likes life is in ConceptNet, right? So you have this very kind of uneven and unusual coverage in ConceptNet, but it's large enough that we're actually able to get some traction with it. And so these are really, and then because ConceptNet is particularly lacking in taxonomic relations. Those are the kinds of things I guess people just don't think to type in if you just ask thousands of people to type in sentences. We combine ConceptNet with WordNet, and WordNet gives us a lot of taxonomic relations. And so here we see that, if an avoider is capable of receiving an action and attack verb, well, that avoider can be used as a role filler if I can also find an attacker that's capable of that attack verb, or an attacker that's a kind of projectile that's capable of receiving action, the attack verb. So this is handling the case that like a bullet is not capable of shooting, but it's capable of being shot, right? And so and a bullet could still be an attacker in a game, right? Because you might literally just dodge an image of a bullet, or we could use the crosshairs, the 2D crosshairs concrete game to realize that shooting game. So I'm, in the interest of time, we actually have a little demo that lets you edit and create these kinds of graphs, and then like basically ask it questions like, I want a game about a criminal and chasing, and it'll generate a series of microgames about criminals and chasing by sampling the game spaces following the constraints. So there's a little demo if people would like to see that afterwards of that working. Yeah, I'm not going to talk about the details of how we sample a game space, other than to point out that this is specifying a space of all possible games, and then what we do as kind of a stand-in for that style of game where there's an exogenous signal that's modulating the game, like a news game. You would have a news topic, right? Might be a signal that's modulating your game, or my web traffic might be a signal that's modulating the design of a game. If I'm doing the game a day thing. So as a stand-in for that, the player specifies a noun and a verb and says, I want a game about ducks and shooting, or I want a game about pianos and playing, or pianos and swimming. I'm not sure what it would come up with, but you could say you want a game about pianos and swimming, and maybe it can't generate anything. I don't know what would happen. And then it basically tries to generate a series of games by sampling from its game space that's defined by the constraints and slipping constraints. So it does do this thing where we wanted to play with conceptual slippage. And so here we have this idea of trying to find the closest satisfying noun and verb roles. So satisfying noun and verb roles would be ones that satisfy the constraints. Closest is measuring those satisfying noun and verb roles to the noun and verb you typed in. And we've got, rather crude notions of closeness defined in terms of hops in ConceptNet, but that gives us kind of interesting semantic slippage. And then we try to present the games in an order of increasing semantic slippage. So if you say you want a game about criminals and chasing, the first games are going to be kind of the obvious games, and then you're going to sort of get weirder and weirder games as you sort of allow more semantic slippage. The interface goal, so this is sort of a screenshot actually from our interface for creating these games. Our interface goal was really to let a designer, or in this case a meta designer, iteratively explore the constraints of the common sense reasoner. And what I mean by that is, common sense reasoning, certainly in its current incarnation, and you could argue about whether it'll ever be achieved in its full incarnation, but in its current incarnation, it's very incomplete. You get very unusual answers out of it sometimes. There's like very uneven coverage and so forth. So instead of kind of requiring that the user kind of learn the full ontology of the common sense reasoner and all of its bugs and quirks and so forth, instead we want to let you iteratively explore the common sense reasoner. Like, let me try these constraints, and then you try the constraints, you see what games you get. Our interface lets you ask why. If you see a role filler like piano and a banana when you said criminal and chase, it's like, well, how am I getting piano and banana? And then you can ask why, and then you'll see it tell you that, oh, well, we're satisfying a ConceptNet query via this chain of relations. And then you realize, oh, okay, well, then I need to tighten that relation, that constraint, right? Or maybe I'm happy with pianos and bananas. I mean, you'd have to decide as a designer. But we wanted a prototype that lets you sort of iteratively explore and work around kind of the inevitable limitations and failures of common sense reasoning. And kind of provide this interactive framework for the designer or meta designer to work in. All right, so jumping to the next area of work we're working on in the space, we've kind of put thematic mapping on the side right now, and we've got our little WarioWare microgame spitting out, and the next thing I might want to do with that is actually see if I could generate news games, like really simple news games from that. But I'm sort of putting it on a back burner for now, and we started working with mechanics. So if you remember in the thematic reasoning prototype, the concrete game which is that it's a 2D thing with sprite pairs or so on, was this like bundled collection of J2ME code, of templated J2ME code. That's a black box. You can't reason about it, right? So now we want to try and open up that black box and say, no, all the mechanics, all the way down, all the state evolution is something that you can reason about and make decisions about. And so focusing purely on mechanics. And we're not worrying about thematic mapping, and we're not worrying about visual representation, just mechanics. And we're using the event calculus to reason about mechanics and state representation. And there's really sort of two applications that are currently driving this work: a game design assistant for expert designers. So not the one for novice designers, but more like the one for expert designers who are doing early stage rapid prototyping. This is kind of the reflective rapid prototypes angle that we're pushing on now, and automated design discovery in the context of discovery systems, except kind of aiming discovery systems rather than at scientific discovery, at discovery of new design tropes. All right, so briefly, what is the event calculus? It's a temporal logic for reasoning about system dynamics. And probably in some AI class, you've all seen situation calculus. Situation calculus is the other big temporal system for reasoning about reasoning about state evolution. We chose the event calculus rather than the temporal calculus, the situation calculus, because we found the event calculus to be, for us, more natural for reasoning about game mechanics. And the big thing that situation calculus gives you that event calculus doesn't, which is a branching time model, it turns out we don't need. And so given that we sort of found it, like for KR purposes, we found it more natural to use the event calculus, and we don't need branching time. That's why we're using it. So what is in the event calculus? It's based on fluents, events, and time points related by these four basic predicates. A fluent can hold at a time. A fluent is basically a time-varying predicate, right? So it's a reified predicate, but for functionally reified predicate, but for our purposes, just think of it as a time-varying predicate. So something can be true at a specific time, an event can happen at a specific time, an event can initiate a fluent at a specific time, and an event can terminate a fluent at a specific time. And those are the four basic predicates that define the event calculus. And the meaning of those predicates is defined by event calculus axioms. So if you actually, you want event calculus, you've got your Prolog shell open, and it's like, I want event calculus. Well, you get event calculus by basically typing in, a couple pages of stuff that looks like this. If an event happens at a time, and that event initiates a fluent at a time, then that fluent holds at the succeeding time and is not released at succeeding times. And so you have a bunch of, not a bunch, like on the order of a page or so, of those kinds of these kinds of event calculus axioms that provide the semantics for holds at, happens at, initiates, terminates, and there is a release step, but we won't talk about that. So how do we apply this to games? Well, fluents encode game state. That's pretty easy. So you can have like, I'm at position XY in the world. Player avatar is at position XY in the world. That's an example of a fluent, because which position XY I'm at in the world is actually a function of time. So the fluent is avatar at XY, and then I can talk about that fluent holding at different times, right? So that's pretty easy. Events encode player input. So every button press and so on is an event that happens, and game state initiated events. So you can talk about collision events happening, player win events happening, and so forth. And then game mechanics are now state evolution rules, where the changes in game state are caused by events, and events trigger game state. So colliding with an enemy, which is an event, causes the player to lose health, a fluent value change. That's a rule that's like really easy to express in the event calculus. Or reaching 100 points, a state trigger, causes the player to win the game, an event. One of the reasons we enjoy using the event calculus is that it's possible to develop idioms for using the event calculus that are elaboration tolerant. So elaboration tolerance means that you can revise, you can make local changes to a theory without having to do global theory revision. So we would like to be able to revise games by atomically adding and removing dynamics, right? Like if you wanted to add the fact that reaching 100 points causes the player to win, what you don't want to have to do is touch like 30 statements in your event calculus representation of the game to put that in there, right? You'd basically just like to add or retract a single statement that says, when I reach 100 points, the player wins. Elaboration tolerance lets you do that. No theory revision and no non-local modifications are what you're aiming for. So the event calculus provides support for elaboration tolerance via inertial fluents. Fluents retain their value unless an event changes them, or they're specified not to be inertial with released and released at. So this is what's called the common sense law of inertia. So once something's true, it stays true until I tell you, till something explicitly says it's not true, and you have circumscription of initiates and terminates. Events only affect the fluents we say they affect, and that kind of circumscription gives you, lets you work around having to have a bunch of frame axioms. So those are, frame axioms would be an example of something that's not elaboration tolerant. Once you have a bunch of frame axioms floating around, then every time you make a change, you have to change a bunch of frame axioms too. All right, so here's an example of a simple tile world, like a Zelda world, for example, represented in event calculus. So we can say, sprites occupy the same XY tile, sprites occupying the same XY tile location collide. So that tells you something about collision in this world. Inventory is empty at the start of the game. The gain and lose events add and remove objects from the inventory. And to use an inventory item, it has to be in your inventory. These 4 statements say that. So now those 4 statements have now just given you a simple inventory system. Right? Collision with an item you can pick up causes a gain event. That's this axiom. And so you can see that you can sort of specify kind of movement, object pickup, and inventory very concisely in these kind of event calculus representations. So this is our a screenshot of our current lovely programmer art demo, where we have a simple tile world, and what we're doing is, in a sense, we view this as one of those circles and arrows prototypes, right? This is one of these circle and arrow prototypes, but it's specialized for tile worlds. So you can create kind of anything you could do in a tile world where there's objects and you move around and there's collision. That's sort of supported by this system. You can sort of save, save game states, plan between states, because we can do, once we have event calculus, we can do abduction to plan, where our abducibles are player actions. We're basically doing player planning. We can do deduction for state evolution. So we've got, both those things. So now we can plan between states, we can edit states, we can watch specific states, and we can change. Here is sort of our stand-in for changing mechanics. Obviously, we don't expect game designers to actually type in event calculus. We'll have to develop some kind of nice interface, and we're looking at developing domain-specific languages to support that. But for now, we just have this thing where you can say, oh, is cardinal movement turned on or off right now? Or do I allow diagonal movement? Is there a time limit? Are walls impassable or not? And so forth. And then you can start answering queries like, is it possible for the player to get to the exit if they haven't picked up the key, right? And which is what you would expect them, is that no, you should be able to get to the exit. You should only be able to get to the exit if you've gotten the key to unlock the door. But of course, if I turn on diagonal movement, you can get to the exit without grabbing the key, right? So that would be an example of sort of a kind of simplified example, but an example of a design bug that could be introduced by changing mechanics, movement mechanics, without altering something about your collision mechanics. So why are we using logic at all? Well, as I just briefly mentioned, logic is sort of giving us the ability to kind of reason forward and backwards about the mechanics, in the sense that we can do forward simulation via deduction. We can do player planning via abduction, and so we can always ask questions about reachable game states, about ways of overcoming challenges, et cetera. So, another question you might want to ask is, given a challenge in the game world, like in your tile world, is there more than one way to achieve it? And if so, give me, show me the player traces. And we can do induction for player modeling. So we can take concrete player traces, either observed or abduced, and build player models, and then have our player models play the game in the forward simulation form and start giving us like statistical ensembles. Like, what percentage of the time is a player able to complete an RPG level if they're playing as a fighter, that kind of thing. Event calculus is really kind of an assembly language of game design right now, and we know that this is not something that even we want to work in too much, because there are really subtle logic bugs that you can introduce. So, for example, implication for rules is a subtle logic bug where here, I kind of said, oh, this says that sprites occupying the same XY tile location collide, right? Or what it also says in a full model of this program is that collisions just happen spontaneously at any time if it's not the case that you're occupying the same tile location, right? Because implication is true whether the implication is true if the left-hand side is false, regardless of the value of the right-hand side, right? So, that would be an example of implication not really quite giving you rule semantics. And so what you really need to do is circumscribe happens, or in this case, circumscribe happens collide. And if you use Prolog's negationist failure semantics, well, that it almost gives you circumscription. But then there's some other problems that arise. You could make this an if and only if, but if you make this an if and only if, you lose elaboration tolerance, because now if I want there to be some other way that things can collide too, I can't just like add it as a separate assertion. I have to go back in and fix this one up, right? Because I had put an if and only if in there. So those are examples of sort of subtle logic issues that you have to resolve. And I mean, they are resolvable. Circumscription is the cleanest way to resolve them. But you have to think about them when you're working in the event calculus. So we're developing higher level sub-languages for specific subdomains of game design. And then we're going to compile those to event calculus. And what I mean by a subdomain of game design is like inventory systems. Inventory systems is a subdomain. So I don't mean genres. I mean these sort of cross-genre cutting concerns, sets of concerns. So inventory systems, and what do you have to worry about with inventory systems? What do you have to worry about in an economy system? And if we could have little sort of higher level domain-specific languages for each of those concerns, then designers can think in terms of those concerns, author their mechanics in terms of those special languages, and then it all gets compiled to event calculus behind the scenes, perhaps in a non-elaboration tolerant form. You don't care if you're automatically compiling to it. I want to talk a little bit before I conclude about the current work we're doing interviewing game designers. So we're doing a series of ethnographic interviews with game designers and as a kind of a requirements analysis process for determining whether real game designers who are currently in the rapid prototyping phase of building real commercial games actually would find something like this useful. Right? So we have 3 different game designers at 2 different studios that we're working with now who are all doing sort of early concept phase rapid prototyping. And Mark Nelson, who's a grad student working with me on this work, is basically serving as the automagical interface between them and an event calculus framework, right? So we're actually coding up concerns that they're worrying about, like with one of our game designers, they have some concerns about their inventory system they're trying to figure out right now. So we're coding up their inventory system in our event calculus framework. It's actually very quick to do. And then we can actually answer real questions about it and see, are these the questions you want answered? What questions do you want to actually ask? Given those questions you want to ask, can we actually support it this way or not? What sorts of interfaces would you want to actually work with this? What does your design process look like? You know, we're actually collecting process maps to understand the prototyping process, because the game design process is actually pretty ill understood right now. I mean, there's lots of game design textbooks that talk about the game design process, but it's kind of a, I'd say, sort of a notional view of the game design process, right? It's not a model of what game design is like based on actual like ethnographic studies of game designers in the wild. It's more like this kind of rational reconstruction of game design sort of after the fact. That's what you can kind of find in books now. So we're trying to understand what the heck is it that game designers really do and think about when they're in that sort of early concept phase to make sure that all this work we're doing with sort of event calculus support for design queries is actually answering the questions and addressing concerns they really have. And the short answer is, I'd be happy to talk with people offline about what we're learning there, but the short answer is that yes, they're actually quite enthusiastic about this, and they get it very quickly. That's one of the interesting things, is that, you know, commercial game designers, many of them, or at least the ones we happen to be talking with, think in terms of sort of abstract game state evolution, and they think of games as kind of systems of formal mechanics. So that kind of formalized way of thinking, they're already kind of meeting us halfway. And they, you know, I've been amazed sort of how quickly in the sort of preliminary meetings we have where we ask if they even want to participate in this study, that they're like, oh yeah, I get what you want to do. That'd be great. I have a bunch of questions about my design I'd love to answer, right? And they seem to, we get traction on the idea right away, which is good, because if we didn't, then we might just be, you know, doing some strange, you know, academic thing that's irrelevant to anybody, right? So it makes me happy that this is actually something real game designers think about. But hopefully we're going to be writing up a paper in the next month or so where we actually talk about the results of these ethnographic interviews. And so I think with that, I'm going to finish. Thanks. Automatic audio generation. There's a growing interest in procedural music in games. And I'd say probably one of the most advanced is actually Spore. 2 years ago at GDC, there was a nice talk on Spore's approach to procedural music. But it's basically at the stage of okay, so for most games, I'd say Spore is going a little deeper at this. In most games, it's a bunch of human pre-written music loops, and then sort of sequencing decisions, dynamic sequencing decisions made about pre-written music loops. In Spore, they've actually expressed all of their procedural music as max MSP programs, where so like a specific rhythm or something is not like some MP3 or some little canned file of some drum machine or something. They've actually got like a little max program. I think they're actually using pure data, PD, but they're using, so they've got a little PD program for rhythm and different kinds of rhythm, and then that program is modulated by inputs from the user interface. And so you actually have sort of rhythm subtly changing over time, melodies and harmonies subtly changing over time, being programmatically generated by a PD program as a function of user interface events. And that's probably the most sophisticated form of procedural music out there. On the academic side, there's there's obviously a literature on automatic composition, but there's not much, or I don't know of any, on real-time interactive automatic composition. And actually at Santa Cruz, David Cope is a professor at Santa Cruz who's very well known for EMI, Experiments in Musical Intelligence, the program that can compile Bach and Mozart music in a style indistinguishable to Bach and Mozart experts from real Bach and Mozart. And so he's been doing sort of automatic composition for years, and he's like doing this kind of online real-time composition is something he's just starting to become interested in, and that there's not much prior work on or any prior work on. So in Facade, the game state is all social state. So it's all, I mean, there is formal game state we're keeping track of, but the formal game state refers to social state and discourse state and so forth. And so then you would need to code up event calculus axioms that describe state evolution of social state and narrative state. We're not starting there. That's obviously, I mean, I think it's pretty obvious that's just harder than physical state, and so we're sort of focusing on physical state right now. Obviously, I would love to grow this stuff into narrative at some point, and I would love to do that, but we're not starting there. One of the things that's nice is that the event calculus is a framework where you can do planning like reasoning in the context of other forms of deduction. And it seems like the sort of old-fashioned green style planning and logic is starting to come back, partly just because I guess of Moore's law. You can actually start planning over some real problems now by planning and logic as opposed to using specialized planning languages. So that's one of the things that kind of excites me about this logic framework. It seems like you could imagine growing it into story planning or narrative planning while staying in an event calculus framework that's also reasoning about like physical events in the world. But no, basically, yes, the short answer is that's far out. Mm-hmm. So right now, like this is the model, that design time assistance is the model we're looking at. Right now, we're focusing on basically answering questions about a design in process. And what we're not doing right now is having our own heuristics where we say this looks good or this looks bad. And we're purposely kind of staying away from right now putting heuristics in the system that purport to make value judgments for the designer. It's kind of this value neutral querying right now. Now, for a novice game designer, I would feel comfortable putting a lot of sort of evaluation critics in there. But for expert game designers that we're focusing on now, it's like, no, we'll let you just do your expert game design thing, and we will give you, we'll answer a lot of queries about your design in progress. So did that answer it? Okay. All right, thanks.